Now we're rolling. So again, welcome to the sixth lecture already. Time flies. Wow. And today we're gonna. So last time we talked a little bit about what was that? Oh, what was last time actually? Anyone remembers? Oh yeah, we talked about language models. Exactly. So and we had yes, thanks. We had text generation and we had language models. We talked about language models and we had these count-based language models first, and then we said, well, there are better ones, for example, the neural language models, right? And that's we finished. And we said neural language models actually learn something meaningful on their way. They learn some so-called word embeddings. So they learn how to map a word, which is one-hot encoding, into something which is more dense. Okay, good. So we're gonna continue in that matter, and we're gonna explore more how to learn word embeddings even better. So what does it mean to learn word embeddings? So here's the task we can solve with that. So if I give you a large corpus of let's say some plain text data, okay, so this is what you get: only plain text data, no labels, nothing, just I don't know, Wikipedia. Can you build a model that will answer any of these so-called word analogy tasks? So word analogy task is, for instance, the question would be Germany to Berlin. It's like France to. What is the answer here? So Germany to Berlin is like France to. What? Paris. Paris, yeah, exactly. Okay, and man to king is like woman to. Yeah, to queen, yeah, exactly. Okay. Can you build such a model that, given any of these analogy tasks, could tell you, or not a model, can you build a system that will be able to answer these analogy tasks? I mean, this is something that you already need to understand a little bit of meaning, a little bit of semantics of things, right? If you're, oh, again, the balloons, come on. Can you disable the balloon somehow?
Yeah, if you go to the path to the bar above and click on the camera there, shows that the software is using the camera and you can disable the reactions.
Okay, I'll do it after the lecture or in the break, so you'll show me. Okay, I like the balloons, but not really so much. It's nothing to celebrate today, I guess. Anyway, so this is basically a powerful model. I mean, if you can answer some of these analogy tasks without creating labels for that. Remember, we don't have any labeled data. It will learn unlabeled. So this is kind of cool, isn't it? If you partly agree, this is great. So you're in the right place. If you disagree, you can go home and just come after the lecture. Anyway, so that's what we're gonna after this lecture, we should be able to kind of solve this task to some extent. Okay, but let's recap the last lecture again, where we finished, and this is the combinatorial graph of the of the neural language model. And what we are doing here is we are taking the previous words. So we took the context, like the previous three words, the black dog, and we're trying to predict the probability of the next word. So it should give us a probability over the vocabulary for the next word after these three words. And how we did that, we basically had this lookup function where this is some sort of a matrix. We call it embedding matrix already. And for each of these words, so what were these words? How are these represented again? What was these words? How do we represent these words? The simplest way of representing word. One hot, yes. One hot over vocabulary, exactly. And the lookup function, there's something that it's basically taking a row in this embedding matrix. And so this is a matrix of size of vocabulary and some other dimension. And it basically took the word, and where the one hot was 1, it selected the row here. So there is coming a much smaller vector here. And we simply concatenated these three together. So one after each other, one of the possible operations, how to get them together. And okay, what is this? Now you should know that. You should somehow remember. So what is this? It has a name. So there's a couple of parts of that. So we have things. I mean, these are obviously nodes and these are trainable parameters, but the whole thing is kind of something which we had in the exercise as well yesterday. Kind of, we ended up with something similar. and it has a name. It has certain things that are stacked on top of each other. In this case, there are just two. So what are these things that we stack on top of each other?
I guess it's two linear nodes. And
yes, we have layers. We have layers. So this is the first layer, and this is the second layer, and we basically building a thing. Yeah, it's a combinatorial graph, but it's representing something, and it's representing the multi-layer perceptron. Basically, a stack of layers. So we have the first layer, which goes to the next layer, and then there's goes to prediction, something like that. Okay. Any questions? So here we have basically one linear projection followed by what was that? So we use some nonlinearity function. What was the nonlinearity we used so far? A nonlinear function. Yeah. Yeah, we had a ReLU, for instance. So for instance, ReLU, it could be also 10H, but we use ReLU, which is like the default. All right. And then there's another projection, and then this is the loss, and this is the gold standard label. We actually forgot something here. Let me see. Oh yeah, okay. So this is it. So this is what we had so far, and we're gonna simplify it for the sake of saving some space here. So what I'm gonna do is just to replace the lookup with the operation. Just call it V. So it's shorter and it's smaller on the on the picture. So this is the lookup operation. We call it V now. Concatenation remains the same, and I packed everything. Here was a linear node with the parameters extra, and I packed them into the node, right? So if you look here, I took this one and just created one single node, and from this as well, so it's somehow clear or shorter. So here there are parameters W1s, the projection matrix, and the biases, and here the same for the second layer. Okay, now it more resembles the layers actually. Like this is I would say it's like maybe an input layer. It could be an input layer or not. It's a layer, doesn't matter. Somewhere in the graph is a layer, and here's another layer. Okay, and this is again operation of the nonlinearity here. Okay, makes sense. So it's just simplifying the clutter here. We forgot one thing, and I apologize for that. Actually, because we're predicting the distribution over vocabulary, which must be shown here. So let me just put it back. Over the vocabulary, we forgot the softmax here. So this is really important because without the softmax, I mean it's wrong here. It produces a vector, but it's just it's not a distribution. So here we need to introduce a softmax basically. So what is softmax doing again? Sanity check. What is doing softmax? Do you remember what softmax is doing? Exactly. Yeah, it's taking a vector of real numbers and create a probability distribution out of it. Exactly. That's what we want because we have the vocabulary of words, which could be, I don't know, 50,000. And for each of them, we need to know what's the probability distribution, because then the gold label is also, so what is, okay, sanity check. What's the dimensionality of the gold label? Again, 50K, exactly. It's the same size of the vocabulary. And how does it look like as a distribution?
Because it is the definite answer, what goes next, it's one hot encoding.
Yeah, so it's all zeros here, and here's one. So it's very skewed probability distribution, but it's a probability distribution. It sums up to 1. It's all positive, and so that's why we can use this thing here. So who remembers what was this here? This function. We want to compare here the prediction from our model with the gold label. And both of them are the same size, and these are two probability distributions. So we had one very special operation for comparing the differences between two probability distributions. Okay. So for a binary task, we had okay, what is this L meaning? What does it mean? It's a loss. Okay, cool. So we're getting somewhere. Good. It's a loss. And we talked basically about only two variants of a loss. One loss was for binary classification, which was the binary cross entropy, right? It was like what was that? This logarithm thing, right? This tiny little formula. And we saw this is a special case of something for more categories, like a distribution over, basically a probability distribution over more categories, which is also called, You have to know that, okay? So it's a cross entropy, but this time it's a categorical cross entropy because we have several categories. So we have a categorical cross entropy loss, okay? So you should remember this. It's very important. So this is the loss which is saying, yeah, how far these two things, like this prediction and the gold standard are apart. And through backpropagation, we learn how should we update the parameters. So what's the error on this particular example, and we learn how to update the parameters. We take a step and repeat on the next sample. Okay, all good. All right, so this is what we had so far. So this was the language model for taking 3 previous words and predicting the next word. Before we jump into the how to make it better or faster or both, we should talk about one thing, and this is the dot product. Okay, so we need to talk about the dot product. It's a paraphrase. We need to talk about a movie. We need to talk about Kevin, which is a beautiful movie from the 90s. Anyway. But let's talk about the dot product first. So what is a dot product? We have 2 vectors here. I'm not using arrows here for vectors, okay? So we have 2 vectors, u and v. They have 2 dimensions, x1 and x2. So what is the dot product of these 2 vectors? How do you define a dot product? What is it? It is a formula. So what is the formula for dot product? We had it already. I guess we talked about a little bit dot product, so maybe you remember, or you should maybe know from linear algebra. What is dot product? Yes.
x1 times x1 plus x2 times x2.
x1 times, again, x1 times.
I mean the x1 from 1 times the x1 from the
Oh, okay, so u1
yeah,
times v1 plus u2 times v2. So this is v. Yeah, exactly. So this is one of the definitions. This is, I would say, algebraic definition. And if you have n dimensions, obviously this is like the sum of this thing. Okay, cool. We also have a geometric expression for the dot product. Anyone remembers the geometric expression for the dot product? Like if we take, let's say this is because we have 2 vectors and there's an angle which I call theta. So if I know these 2 vectors and I know theta, there is something special about the dot product as well. Anyone remembers that? Yeah?
Theta is 90 degrees. They get the dot product of 1.
Could be, okay. Could be. Yeah, could be. Or not. I don't know. Let me okay, I would need to think so. We'll come to that exactly. I think it will be actually 0, I guess. I think it will be, yeah, it will be 0. But you're getting somewhere. So there's a formula which is something to do, obviously, like the dot product changes with the angle. So anything more specific comes to your mind before you look up Wikipedia? You look up Wikipedia. No, it's on the slide. Okay, because you have the handout. Okay, cool. Yeah, that's kind of sad. I mean, yeah, it ruins the storytelling here. But anyway, so here's the geometric representation. So it's taking the cosinus of the theta. So now it gives us the answer to what is the cosinus of 90 degrees? 0. So then if there are just 2 vectors have a so-called right angle, then the dot product will be 0, not 1. What is this? What is these things? What is that? It has a name. So do you recognize this symbol?
I recognize it as a norm in a normated space.
It's a norm. Yeah, it's a norm of the vector. Okay, cool. So what is a norm of the vector? Yeah, you?
It has the same direction but length of 1.
You're answering well, but a different question. Keep this answer. It's something else, but we're getting somewhere. Okay, so yes, this is something else. But what is a norm of a vector? If I say it's a Euclidean norm, it should ring a bell. Euclidean norm, what is it? There's one word, it's the length. It's the length of the vector. Okay? If we have a vector v, a vector u here. Oops. Okay. Yeah, this is its Euclidean norm. So how do you compute a Euclidean norm? How do you compute a length of a vector?
Of the elements squared.
Yes. And so on. If you have 2 dimensions, we use a Pythagorean theorem. This is it. This is it. Like in n dimensions, it's just the Pythagorean theorem in more dimensions. But basically, it's Pythagorean theorem, right? You take this triangle, square it, and take a square root. Okay, so there's no magic. Okay, Euclidean norm. Okay, so this is the length of the vector. This is interesting. So it says that the dot product is a product of the length of these two times the cosinus of the angle between those. Okay, this is interesting. So it has something to do also, because here, if you look at this, what is the meaning of multiplying 2 numbers in dimensions? Well, maybe it's not really clear, but here is to me at least, it bears some more meaning, because cosinus of the angle, I can imagine like 2 vectors having an angle and being close to each other, smaller angle or far each other. So it has a meaning, and it will be super helpful to understand the dot product. So this is it. So this is our algebraic and geometric kind of representation of the product. Now, what we can do also here is that if we have so here we're having this u and v vectors, and we can project the u vector on the v vector. So the projection means like I'm putting it here with the a triangle. And also the length of that is basically the dot product over the length of the v, right? So this is the projection. If you do a little bit of trigonometry and algebra, you'll find that we can project one vector to another, and this result is showing like how, I don't know, the strength of the projection, but where do we project one vector to another, right? And you can do it the other way around. You can project v on the u, and this will be the length there, basically. So this is the scalar projection. Okay, so it shows basically how, what does it show? Something interesting. Think about it. Anyway, so we have this projection. Now so this is a recap from sort of mostly high school, I would say. Now we have something you answered already, and this was a different question. It was a unit vector. So what is a unit vector? You said it has length of 1 and has the same direction, right? So you answered what is a unit vector. So unit vector is something that that basically has a length of 1. And how can you imagine unit vectors is that we kind of inscribe them in a circle. So this is a circle of radius 1, which means every vector which is somewhere here will have a Euclidean norm of 1. Okay. All clear? Good. So these are the basics. Now, if we have unit vectors, what happens with their dot product is that, well, these two becomes 1, right? Because we have unit vectors, so we get that the dot product of unit vectors is just the cosinus of the angle. Ah, this is interesting. Okay, cool. So if we have 2 vectors which are just 1 unit long, then the dot product is turning basically into something which depends on the angle. This is cool. So it shows like if you have 2 vectors in 90 degrees, their dot product is 0 and so on. So we have I guess I have a function here. Exactly. So for instance, here these 2 vectors u and v. So this is their dot product, 0.7 something. So the cosinus theta of any angle, basically, cosinus ranges from -1 to 1. Okay, so we can agree on that. So it's a trigonometry, and how it looks. There's sinus, there's cosinus, so cosinus starts with 1 for 0. Okay, so this is what you should remember from high school. So we have this for these two vectors. We have some positive here. We have some positive cosinus, so positive dot product. Now we're coming to your part. You know, if they're orthogonal, so to say, so 90 degrees angle, we're here, so we're getting a 0 dot product. Okay, and obviously, if we have a vector which points to completely opposite direction, like really 180 degrees in these two dimensions, or opposite directions in n dimensions, there are so-called, like, I would call it like least similar in a way, but similarity is it's just a multi-semantic word. So similar in terms they're pointing completely to the different two directions. Okay, the product is -1 if they're unit vectors. Okay, does it make sense? So if you have two vectors, so my hands were two vectors, this is like this would be like 1 dot product. I'm moving apart 0 to -1 and back to 1 again. So it says something about how similar these vectors could be if similarity means pointing to similar direction. Okay, so we can utilize this kind of notion of the angle, which will help, or the dot product, which will help us to understand it better, maybe, or to visualize it better. Okay, any questions so far? Good. This is really recap, but I wanted to be really on the safe side that we understand the geometry behind that, because then you get more better intuition about the dot product. The thing is that the dot product is also, so the product as we have here is unbounded so it doesn't have a bounded range. It could be anything. So we have these two vectors, and now we know, okay, the dot product is greater than 0. Why is that so? Because the angle is smaller than 90 degrees. Okay, so they're pointing in some direction, so it's more than 0. Now we have another vector which is pointing the same direction as v, but it's just larger. Well, the dot product becomes also larger, right? Because the dot product takes the length of the vectors into account. So this will be these two vectors, u and w, the product of them will be larger than the small vectors and u and so on, which means, the larger we get, the bigger it gets, and basically it's unbounded, which means it goes to plus infinity almost. Okay, so the dot product could be anything on the positive side. And the same, okay, so here we have u vector and y. Of course, now it's larger than 180 degrees. And it's actually, where is that? U and y should be actually, no, it's not 0, it's negative. It's negative, I don't know what is it, because I don't know the length of those. If it's a unit vector, it will be -1, but it could be something else. But it's a negative because the angle is more than 90 degrees. But again, if we are extending here another vector, which is larger than y, so this becomes much smaller in negative terms than these two vectors. So again, it bounds, it goes basically to -infinity on the left hand side. So -infinity, it's unbounded, right? I mean, you can make the vectors larger and larger, and it's unbounded. Okay, so this is it. So there is no, I mean, if we have unit vectors, this is nice because we have the range between -1 and 1. But if we don't have the unit vectors, it could be anything. And you might be asking, okay, what is Euclidean distance? So Euclidean distance is how far, so if this is one point and this is another point, what is the Euclidean distance between those two? What is distance between 2 points? Yeah. Yeah, like this is the distance, right? This is Euclidean distance between two things. And now we see that we're actually changing by changing the product is changing, but we're also changing the Euclidean distance between all the points. So maybe there's some relation between cosinus, between the product and Euclidean distance, right? Is there any or not? Let's find out. Let's find out. Because if you think about distance between points in a space, you basically measure, you take a line between these 2 points and measure how far they are. This is Euclidean distance. If you have two vectors in a space which are also points, vectors are basically a representation of points with the origin, you can think of distance as, again, as a dot product, taking the angle between these two into account, right? So we have two views on distance between points. One is taking the vectors and looking at the dot product and looking at the angle and the length of the vector, and the other is basically looking at the point directly and measuring the distance between them. So is there any correspondence? Well, let's see. So Euclidean distance is basically this. It has this formula where you, for each of the points of the vector, you subtract them, take a root, and then this is just Pythagorean theorem again in practice. So this is how you you subtract two vectors and make its distance. So let's take a square of this Euclidean distance. So if I take this Euclidean distance, or also L2 norm, but Euclidean distance is fine. I take this definition and I just get rid of this this square, excuse me, the square root, and I'm here just create, I'm just making explicit squaring of these. Okay, so this is a little bit of algebraic operation. So everybody follows so far? Good. I'm not gonna write it per hand because my writing is horrible and the LaTeX looks just better, So if this were like mathematic lecture, I would just draw it on a blackboard and nobody could read it. So now what I'm doing, I'm just multiplying these two terms, just make it very explicit. So just multiplying each with each other. So it's just, again, a simple algebraic operation. What I'm now going to do is use the, what's this, distributility? Well, I don't know these terms. Well, anyway, this is a sum of pluses. So I'm gonna just, add the sum, put the sum between here and here. And what I'm getting here is interesting. So this is now we're getting back the definition of a dot product between u and u. Here we're getting a definition of the dot product between v and v, and here we are getting a definition of a dot product between u and v. So we're simplified back to dot product of u, dot product of v with itself, and two dot products u and v. Okay, so if these were unit vectors, if u and v are unit vectors, we're getting their Euclidean distance is 2 minus 2 times u and v. Okay, so there is a clear formula for what is the distance of two vectors and what's their dot product in terms of the angle they're taking. Okay, so there is some correspondence. And also, which means that minimizing the squared, this squared Euclidean distance, so minimizing squared Euclidean distance is proportional to maximizing, right, because we have minus here, maximizing cosine similarity. Okay. And it becomes not proportional, but equivalent for unit vectors. Okay, so what does it mean? If I want to push two things together, two vectors together, I can either minimize their distance, right? On a space, I'm on a space, I want to put them together, so I need to minimize their distance. Or I'm gonna maximize their dot product. This is the same operation. Does it make sense? If I want to push two things together, I just minimize their distance. If if this is something I can optimize for, I'm trying to push them together by taking small distance, or equivalently minimizing their dot product. This is going to be super helpful. So do you get this intuition a little bit better now, what we are trying to do? Why to hassle? I mean, you don't have to remember this because basically you can compute it by, it's a little bit of algebra, but the meaning here, so like the intuition here, why it holds, you can prove it why it holds. So why are we interested in maximizing dot product? Or in general, what dot product is telling us? The dot product is telling us how far 2 points are to each other, but also taking into account their length. Okay? Any questions? All right. Yeah, here's a tiny little detail which I forgot. So obviously there's a difference between dot product and Euclidean distance, because if you move the origin of your space, like you have two vectors here, and this is the origin, and this is a Euclidean distance. If you shift the origin somewhere else, oh, this is a bad example, sorry. No. if you shift the origin somewhere else, well, the distance won't change, but you get new vectors and they probably will change their dot product as well. Or if you move it somewhere even more extreme, like if you move it here, then you have almost similar vectors, but the Euclidean distance remains the same. So this is important. Like this is Euclidean distance is invariant for origin shift, not a dot product, but it's just a detail on the side. Anyway. All right, so this was this was trigonometry, algebra 101, Friday morning, so to warm a little bit, and now we're coming back to NLP, back to words. So we're going to be talking about distributional hypothesis. And we tackled it already a little bit when we were talking about the one-hot encoding. So recall the one-hot encoding of words. What we have is if we have a vocabulary of, let's say, 3,000 words, and we have, each word is associated with a position in this vocabulary, in this vector, then one hot is saying, well, nice will be all zeros, and here's going to be 1. Pleasant will be all zeros, and maybe on other position it will be 1. And horrible will be also all zeros and will be 1 at one position, which is somehow corresponding to, to the position in the vocabulary. The thing is, nice and pleasant, we are talking actually about the Hamming distance, right? Between these words. It's all the same. So the distance between these two words is in Hamming distance is the same as between these two words. So basically each words are sort of equal in terms of their distance to each other, right? You need to change 2 bits to get from here to here, and 2 bits to get from here to here, and 2 bits to get from here to here, and so on. But what we want to do, what we want to model, if if you do sentiment analysis, for example, and you see a movie, you see a movie review, no, hotel review, okay. And in your training data, you see it was a nice experience. Yeah, or it was a nice it was a nice stay in this hotel. This is what you have in your training data. So you see the word nice, and you learn your classifier and saying, well, this was a positive review. Now during test or during the prediction, you will encounter a sentence, yeah, we had a pleasant stay. So you just changed one word basically. We had a nice stay in the training data, and during testing, we had a pleasant stay. If you use just one hot encoding of words, you don't know that these two things should be similar. You learn nothing about the similarity of these words, but what you really want is to model the word pleasant similarly as the word nice, and maybe even in this context, but even like context dependent. These two words are similar. You want to capture this analogy, right? So how can we do that? I mean, we cannot do it with this one hot encoding. So we need to do something better. Yes.
Doesn't the embedding give us similar properties?
And these embeddings give us similar properties. That's what we want. I mean, I'm just talking again, making these drawbacks explicit with like one example where we really want to capture these analogy, not to solve these capital, France, Berlin, Paris, and stuff like that, but just in a praxis, like for sentiment analysis, for example. And the embeddings should tell us why. They're based on the so-called. Don't look at the slides now, okay? Don't look at the slides. No, don't look at the slides. I no, come on. It's like you don't think about the white bear, so everybody thinks about the white bear. Okay, so don't look at the slides. We have a distributional hypothesis, which comes back, dates back to linguistics to the 1930s, 1940s, and it says that words are similar if they appear in similar contexts. Okay, so this is the distribution hypothesis. Everybody knows that. Everybody's using that. I mean, we're humans are just, we're using this knowledge. Intuitively, when we encounter a sentence with an unknown word, such as the word Vampinyuk, okay, so now okay, let's make a poll. What do you think is a Vampinyuk? What is a Vampinyuk?
Sounds like an imaginary creature.
Sounds like a creature. Okay, this is interesting. Sounds like a creature. Cool. Any other suggestions what could be Vampinyuk? Why does it sound like a creature?
Yes, all those Marvel creatures.
Yeah, okay.
Have imaginary names, and sometimes
it sounds like that, yeah. So if words, yes. Actually, it sounds like, I mean, this doesn't exist. The word doesn't exist. Maybe now it exists because it was learned in the, you know, if you ask GPT, it will know Wampanyuk because it's in the training data from the book from Yav Goldberg, which I took the example from. But anyway, so Wampanyuk is not a thing. But now, if I show you a sentence, Marco saw a hairy little Wampanyuk crouching behind a tree. This is exactly what you expect, like a tiny little creature. And now you know, Wampanyuk doesn't exist, but what is a Wampanyuk now? It's a tiny little creature, like these, how was they called? Well, some other, you know, some sort of squirrel, and it's in, you know, behind a tree, and it's hairy, like a tiny squirrel, and maybe it's blue. I don't know. I mean, just you know. We infer the meaning of the word based on the context in which it occurs, right? If you don't understand a thing, I mean, you learn basically like by listening and talking, and if there's a new word, you understand the context, so you kind of infer the meaning of that. That's how humans possibly work. So this is cool. Yes.
Big problems because sometimes we have the same context, but the semantics of a word are drastically different.
Absolutely.
For example, words like good and horrible, you could put them in front of yeah, the exam was, and it's the same context, but it has a drastically different meaning.
Obviously, yes. You can have different. So how was it again? You have the same word. No, you have the same context, but you have the same context, but different words, and they carry different meaning. Yes, of course. I mean, where you know the meaning of the word already. No, this is a good question. So if you had like the exam was horrible and the exam was great and horrible are different things.
Yeah, but
they fit in the same context. So that's the thing, like what is a similarity? So it really you come to the issue like, okay, so what is the similarity? What does it mean? In your terms, the similarity would be really syntactic similarity. So bad and horrible, great and horrible, the exam was horrible and the exam was great. Great and horrible have the same syntactic kind of function in the sentence. So it's the adjective of this, you know, in the sentence, and you can replace them, but they don't mean the same thing. While in this case, if you replace Wampanyuk with Tamagotchi, I saw her little Tamagotchi. Do they have hairs, Tamagotchis? Oh, cool. Okay, I saw her little Tamagotchi crouching behind a tree. If you didn't know what Tamagotchi is, but you know what Wampanyuk is, you would kind of infer, okay, this is the same, you know, same creature, or the other way around. So similarity is really something which is not cut in stone, and we somehow like define it as we go ad hoc. Yes.
In that case, like similar words for good are still near good. And
yes, that's what you want.
But there are words, for example, in German, there's umfahren and umfahren, which is the same word for the opposite meaning. Driving over you and driving around you.
Yeah.
So what do we do in those cases?
Yeah, we have to do something much better than what we are talking about today. And I guess later I have these kind of drawbacks of these word embeddings, because there are what do you know the term for this? Like you have the same word with multiple meanings. I think it's polysemy. You have the same word, but it has like more semantics. So polysemy, I guess, is the term. And obviously this is not only umfahren. There's like in English, I have the examples later on. So we are running into troubles, but you had a great idea. Yeah, of course, some, you know, bad and good and well, if you have just this one context, bad and good will be similar, but also you will have like good and nice and pleasant and so on also in there, because we're gonna learn this from the data, learn this from the great amount of data, which gives us a like strong signal what should be similar or not. Okay. So the simplest thing how you can learn a embedding of a word is you create a word context matrices. So, and there's a long line of research on that, like before deep learning took up in late 2010, where you have a word, so you have a matrix, and well, this is just a simple embedding matrix as we had before. So this is the size of the vocabulary, okay. And each is, so there is a word like a Wampanyuk and stuff. We should ask really. So does somebody has like an account at DALL-E or Journey or no, how's it called? Like the generators, DALL-E, image generators. Do you have an account? Anybody? Can you create a picture of Vampinuk, please?
Live now, I Stable Diffusion locally.
Stable Diffusion, okay, locally. Anyone?
Yes, I can access it via thing.
If somebody can create a picture of Vampinuk, which we can show at the end of the lecture, it'd be awesome. So just send me a link. I want to see how, what DALL-E thinks about Vampinuk. Okay. But anyway, so we have this matrix, and again, so each row is basically a word. And then what should be in the context here? So we can put anything we want, actually. So the row, each row could be any linguistic context. And maybe we're saying, well, the context should be, the words in which the target word occurs. So maybe neighboring engrams. So here, this could be maybe I was. The second row could be I am. And very many thousand or 100,000s of engrams, for instance, because you have a context and then you have the target word. So I was Vampinuk, or I am Vampinuk. And then what you do is you take a large corpus and just counting how many times you see the word in this context. So you count how many times I saw I am Vampinuk in your corpus. Would be perhaps 0, but who knows, maybe 1. And maybe others like I go home would be like 100,000 times. So you would fill like here, and you would fill the matrix by counting these numbers. What you get eventually is for each word, you get a vector with counts. And maybe for similar words, you get a similar counts because they occur in similar contexts. So basically, you're just counting the occurrences of the word based on the context which you define. That should be actually easy to implement. So does it make sense? You're just looking at the context, could be n-grams, could be anything you want, but typically n-grams. Could be even like left and right. You can like look at a word on the left and word on the right. Why not? You can do that. We're not building a language model, we're just looking at the co-occurrences of words. So you look at the context and then just counting how many times this word occur in the middle, and you get counts. And they will have some properties, and they will have maybe some good properties of the similarity, okay? Because similar words appear in similar contexts. That's what we are trying to model. Any questions to this count-based matrices? So why is it, I have a question. Why is it a bad idea? Well, it's not a bad idea, it works, but how we're gonna struggle with something. Okay, it's huge. The n-grams.
I have to take all of them from my text.
Yeah.
And the combination I will get.
Yes.
That's basically ginormous.
Yeah, it's gigantic. Yeah, it's huge. So it's gonna be huge. Okay, huge, super huge. Also, it's gonna be another thing. So huge is good. So we have a huge thing which we need to estimate. What's gonna happen? What's gonna happen? We have a huge table like 50,000 times 50,000 squared, which is a lot, which is 50,000 cube. So these are basically the parameters. We're estimating the parameters. The parameters are just the counts. What's gonna happen if you wanna estimate like 50,000 cube parameters? You won't have, yeah. You don't have enough data to estimate. Like very many of these combinations will just never appear. It's the same like with large n-grams and language models. If you want to learn like 5-gram language model, you're going to struggle. This is the same thing. You have sparsity, data sparsity. So many of these combinations will never be seen or will be estimated poorly. Okay. Anything else comes to your mind which could be an issue? I think these two are basically pretty much the main argument against these things. Okay, yeah. So data sparsity. Some entries in the matrix may be incorrect because we didn't observe enough data points. Exactly. So you learn some counts, but well, maybe that's not enough to get like a robust estimate of this embedding. And the very high dimensions. Yeah. So that's what you said. We can use some dimensional reduction techniques. If you did some machine learning, you maybe heard of singular value decomposition, SVD, for making a rank of the matrix smaller, but we won't tackle that. So there are some tricks you can do to reduce this matrix, but it's the sparsity remains. Okay, so we have count-based methods. Maybe we can do something better. This is like a analogy. N-gram language models to narrow language models is like count-based embeddings to narrow-based embeddings. So we're gonna use neural networks to learn better embeddings. Okay. So we want to learn representation of words in context, and this is what you said already. Some of you said it, like we had it. Yeah. Remember the narrow language model from last lecture, or we just also refresh it today? So this is again the same figure as on slide 3 or 4. And here, this embedding matrix, it's actually when we train it on some, this next word prediction, it learns the representation of these words in context. It's learning the embeddings. That's what we want. Okay, so we've seen that how to do it with neural networks. You can build this. So you can learn representation embedding of matrix with that. What was the okay? So the embeddings matrix again, it has a dimensionality of, so this is what again? What's the size of the embeddings matrix? Again, the size of the vocabulary. It's your favorite answer, and you answer the same. Good. Get a hatred, get the third one, and you get a bonus. And what is the dimensionality? So here the dimensionality of this matrix was all the possible contexts could be large. Okay. What we said is the dimensionality here. It might be number of categories, but in this case, in the narrow language models, there are no categories. There's no categories. There's nothing. So how do we? Yes.
If we just define it.
Exactly. We just define it. We just say it's gonna be 100. Yeah. So D is gonna be 100 because why not? Like we empirically set up the size of that because everything else will work. Because we're designing, so the size of the layers and the size of the embedding matrix this is a design choice. We can just design it. So it doesn't have, because they don't represent anything existing, like anything in the so-called like real world. They don't belong to categories. They don't belong to anything. This is just an internal design choice of the network, and we can design it as we want. So we don't have to. Yeah. So your question.
Can we say the bigger D we choose, the concreter we can differentiate the different words?
Yeah. Okay. So this is a good question. So the bigger D we choose, if it resembles anything with the real world. So let's say if you have like 100 dimensions only, then the meaning of the columns is more fuzzy, and if you have like 1,000 dimensions, the meaning of the columns will be more. I don't have an answer to that. It's a valid idea, but it really depends how you evaluate what the column means. So of course, if you have more, it can possibly learn more categories, but there is no guarantee in that because, well, you're putting no guarantees, you're putting no supervision here. It can learn anything it wants to make this task work. I get you. To make this task work, the task here is to predict the next word. Whatever it learns, you cannot influence it. It will learn some parameters, and some parameters might be more useful than the others. Maybe less dimension could be more useful for this task, and more dimension will be just maybe redundant or whatever. But you cannot really directly influence it unless you put some supervision in there. You have a question?
We generally know there's more space in the D+1 dimensional space than in D.
Yes, there's more space in D+1.
Yeah, so you can spread points more farther apart.
Yeah, sure. You can spread. You have more dimensions, and then you can have you have more representational power in these embeddings, of course. And everything comes also with the cost of, well, if you have 1,000 dimensions, you have much larger amount of parameters you have to learn. So maybe you don't have enough data. So it's really like trade-offs between the sizes of these parameters, what you're gonna do with them, how you're gonna evaluate them. So typically, you're around like in the hundreds or maybe thousands of parameters, roughly in these static word embeddings. This like empirical observation. Because if you use the standard, here, the SVD, you always go also from like to hundreds of dimensions, and we don't have to do any SVD here. We just design the embeddings matrix as we want, and it will kind of learn dense representation of these words while solving this task. Okay. So this is great. How about making short break now? Sounds good? Or you're still okay without coffee or stuff like that? There is no coffee, I know. Okay, so let's make a short break, and we start at 9:15. Okay.
So we disable the reactions because we're creating balloons all over.
I love the balloons. After we finish, I don't want to screw up the recording here on a.
I don't think you have to. Maybe you can just click the purple.
Let me see.
So
let's move from narrow language models, which do train word embeddings as a byproduct, to actually trying to learn good word embeddings, or faster or more. So, because the narrow language model's goal was to predict the probability distribution over vocabulary for the next word, conditioned on the previous words. Right? We take I want to go, vocabulary, and probability for each word to happen, which like home should be more likely and the others not. Okay. So as a byproduct, it learns some useful word embeddings. But what if we don't care about predicting the next word probability? What if we don't need a probability distribution? We just don't need that. And what if we just want to learn word embeddings? Right? So we don't care about, if I come back here, we don't care about all that stuff. We don't care. We just care about learning this. Learning word embeddings that will work best by our definition, what best means. We can do one thing. We can do two things, actually. First, what was the Markov assumption? Yeah, the Markov assumption was that we look at K previous words only. Okay, so we took a context like previous 3 words only, but we cannot go farther because it just, the model grows too much. So we cannot do that. And also, for language models, we didn't look into the future. We never look into the future. We never took context from the future because we're saying, yeah, okay, you're typing words and you just want to predict the next word and the next word, so you don't look into the future for the context. But maybe, the sentence with the Vampinuk, I saw a little hairy Vampinuk crouching behind a tree. If you remove the Vampinuk but look at the context, before and after, you will see you will kind of make this picture of this tiny little hairy creature behind the tree without a pen, because it would be like I saw a tiny little Vampinuk with a pen crouching. So you can utilize both contexts to learn better embeddings of the word. And we were talking last time about it's like costly normalization in softmax, because it's more like an engineering perspective. In the softmax, you need to take exponentiation of all these terms, and if you have vocabulary of 50,000, oops, my cable is too short for that. So if you need to take all these elements and do this exponentiation over and over, it's costly computationally. So there is no speed up of that. So maybe we can get rid of that. So how can we relax our Markov? But let's start with this. Let's just get rid of the Markov assumption. So here's simplification number 1 of the language model, of the narrow language model. We just did the Markov property. We just don't care. We're going to look into the future. So here we have the previous context, like then there is the target word, the missing word will be in the middle, not at the end of the sequence, in the middle, and then there's a context afterwards. So for example, the black dog, instead of modeling the black and the next word, which would be a dog or some other word, we're going to model the and dog, and we're going to kind of trying to predict what's in the middle. Can we do that? Yeah, we can do that. Why not? So is it like Markov, nth order Markov model anymore? No, it's not. But that's fine, because we don't want to predict probability of word. We're going to learn word embedding. So we're shifting our kind of objective. So now, exactly like more concretely, instead of modeling probability of word at position 3 given word position n1, we model probability of word position 2 given word position 1 and v3, and this is the empty, the empty box, like what we are trying to plug in. Okay, so we're shifting the objective here. Okay, this is great. So we have the previous context, which we're gonna concatenate, and then we have this word. Okay, let me just. Then the other thing which we're gonna simplify is the costly probability distribution, right? Because now here we have the softmax, which gives us this beautiful probability distribution over all words in the vocabulary, and maybe we don't need that. We don't need it. We need maybe something easier than having these and then 0 and 1 and cross entropy loss and stuff like that. So because it basically here it's saying how it's scoring our predictions versus the original word. So it takes some sort of like these distributions, we want to make them as similar as possible. If we're training a language model, we want to make these predictions as close to this gold label, right? So we're kind of trying to make them as close as possible. And the score, we're using here the categorical cross entropy, but it's a score of similarity of two distributions. But it's a score. So maybe there's a better score, which takes a vector and another vector and computes some sort of like similarity. And now we're coming back to what we have in the beginning of the lecture. We had this dot product, and that's why it's going to be very useful here. So we need a score that, given some context and a target word, give me some better score if they're closer to each other, or this is like the correct one, and if this is not the correct one, then some other, some other score. So what we're gonna do is that our model should prefer words in their true context. So what does it mean in true context? We have a sentence, well, could be an adjective for a dog. The cute dog, well, no. The wild dog barked. And so if dog is the target word. Okay, so I have a previous context, the wild and the barked. And then if the word, so if dog is in its true context, like the wild and barked, we're gonna score it high. And maybe if we have words in their untrue context, I'll come to that later, we don't wanna score it low. What does it mean is that we can create maybe the wild cat barked. Of course, if this is the target word and this is the context, this should be some lower score, right? I mean, we cannot predict like cat bark. This is obviously wrong. So it will have like low probability. Okay. So this should have lower score. It's not dissimilar from the neural language model if we take the previous and after context into account. Basically, if we're going to predict like the missing word, and we should choose between a dog and cat here, the dog should have larger, higher probability or higher score than the cat, because cat is more unlikely to happen here. Okay, does that make sense? So we're going to penalize words which are kind of untrue and prefer words which are sort of true. So we're coming to the core of this method, how we're going to tackle that, because we're going to create a negative samples. So instead of predicting probability distribution for the target word, so what is predicting probability distribution? We have the 50,000 vocabulary, and we need to do the softmax to get the probabilities for each word. No, it's a very costly task. We have like 50,000 categories to choose from. We're gonna make it a binary task. So a single output neuron, a binary task. We create this task artificially by choosing either the correct target word or some random incorrect target word. Okay, so we're gonna say the label of our example will be 1, so positive, well, 1. So we have in binary task, we have 0 and 1, right? So it's gonna be 1 if, let me see what's okay. If the word, given its context, is the positive example. So it means it was seen in the corpus like that. And then it's going to be 0 if the target word is a negative example from the corpus. What does it mean? So I'm going to create here our data, our task artificially. I take a sentence, for example, the wild dog, oops, I cannot write, sorry. Dog barked loudly. Okay, and this is going to be my target word. And I'm going to say for this context, with dog, this is going to be labeled as 1, right? This is a true context. This is a positive example. I saw it in the data. I'm saying I'm going to predict the dog here. I want to see dog in this context. So this is going to be 1. And now I'm going to create a negative example. For example, I'm going to replace the dog with some other word. Maybe cats is not a good example. I'm going to replace it with something else, like, I don't know, car. Yeah. So the wild car barked loudly. It doesn't have to be a noun even. No, it's going to be 0. Okay, so it's just, I just replace the target word by something random. It could be anything. It could be the wild, nice. It doesn't make any sense, but it could be any word, right? I can really sample any word. So the wild, nice, barked loudly. It makes no sense, and that's why it's negative example. You know, it should be scored like 0 because it's not something which should happen, and we want to penalize that, and we want to predict that this word is actually occurring in this context. Okay, so if you remember the count-based methods where we are counting when the word occurred all the time, now we're doing something maybe similar because we're giving positive feedback to the model that the word actually occurs in there, so some of the counts, but we're also penalizing if the word doesn't occur in there. We're saying, well, the word should never, I never saw this word here, so you should maybe score it, you know, score it lower here. Okay, any questions? Yes.
And I have to be careful with choosing the random set I get in my phone.
So where do you, so the question is like, how do you sample your negative word?
Because if I have another creature that barks, wolves, for example.
Yeah.
Then.
Yeah. If so, you're saying if you here do something, you sample randomly the word, but if by chance you sample something which makes some sense, you will still penalize it, right? That's a great question. The thing is, you can how do you sample? So you can take the vocabulary, but you wouldn't basically sample uniformly. So you know you have the vocabulary, and you can take basically uniform distribution. So each word will be sampled with the same probability. You know that you can do that. And in this case, you're running into troubles because with probability 1 over V, you can pick any word and it will be like you switch dog with wolf. So you don't want to do that. But typically you don't do that. You're changing this to the probability of each sample. You're changing to some weighting. Oh, what is that? Actually, it's still uniform, isn't it? No, it's taking the frequency. So it's taking how many times the word, each word in vocabulary occurs, and it's normalized. So you're basically the more frequent words, if you sort them by frequency, which means frequency. So this is from high frequency to low frequency. So these will be like D, I, M, and here will be some other words. And then you would say like, okay, these are more likely to happen and these are almost not likely to happen. So you're shifting the distribution from uniform to some more informed about the actual frequency of the words. Does it make sense? Does it make sense what we're doing here? Like we're not sample just here's a vocabulary and take any of them, but we were saying, well, some words which are more frequent have high probability of being sampled. Then the probability that you sample really something which is which is the synonym maybe is very low. So empirically, it won't break anything empirically. You want, I mean, it can happen, of course. It's inevitable because you introduce random sampling, but it doesn't, it's negligible actually. Because you're sampling more examples, actually, more negative examples than positive ones. So it will just, be ignored later on.
So my goal here, separating things that are opposites or making the distinction more nuanced, because if I do that, then okay, I don't get random garbage out.
Yes.
I also don't get better.
No, okay. So you really wanna make sure that your model can predict this word appears in the context, and this random garbage word doesn't appear in the context. This is what you want to learn. So you create examples for that one by just taking this part of the corpus, like the wild dog barked loudly, and then you introduce some fake data, like this fake negatives, by sampling random word. And the sampling of random word could be uniform, and it will work, but empirically, it's been shown like if you take the corpus frequency, it will actually make better negative estimates. But you want to distinguish between this is a true thing which happened, and this is a bad thing that never happened, that should never happen. Okay, does it answer a question? So is everybody fine with this kind of artificial task? So we're basically creating a self-supervision, okay? Self-supervised task. Yeah, we're saying it's like a neural, it's the same like a neural language model. We're saying, okay, given this previous input, give me a probability distribution of the next word. Now we're saying, given context and a word, tell me 1 if this is true, and give me 0 if this is fake random word. But we're taking this from a unlabeled corpus. We don't have to create any labeled data. Okay, so this is very important. Like we are simplifying from predict me next word from 50,000 options to does this word comes from the context or not? 0, 1. It's going to be much, much, much faster because you don't have to predict like 50,000 categories and do the categorical cross-entropy loss. You predict 0 or 1, make a binary cross-entropy and call it a day. So it's going to be much, it's the one simplification we are doing, like the second one. The Markov assumption was like, oh, I don't care about the previous, I can look into the future and model the context in any ways I want. And the second one is, I actually don't care about the probability of the word. I just want to say, is this word happen? I mean, did this word happen or not? Okay. Any questions? Can you create this data by, if actually create me self-supervised data for learning word embeddings? Were you able to do that? Most likely a little of programming, but like intuitively. You just take a corpus, chunk it into pieces, take a target word, and either keep it there and call it, oh, this is 1, or flip it to some random word and say this is 0. This is how you create your data. Cool. So we have this negative sampling, and this is really this is game changer because it doesn't rely only on the things that happen, but also things that shouldn't happen. Like so the chance that you introduce something which makes sense, yeah, there's a chance, but most of the time it's just garbage and it will be 0. So this is great. So we turn our problem into binary classification. Oh, okay. So now remember here we had this language model. What was that? We have this costly softmax and this categorical cross-entropy loss. We don't care. Now we turn it into what's coming out of here is the real number between 0 and 1. Yeah, this is what's coming out of here. So we have a sigmoid here, and this is going to be just a single standard binary cross entropy loss. And okay, here it's showing the example. So the black dog, and here the black is the true word, the positive example. So I'm saying the label here for that is 1. Okay, so this is actually showing the whole network with the positive example. So this is positive. And that's why I'm saying this is 1. Okay, so this is really a positive example because it happened. Like the black dog was in the data. Okay, makes sense? Any questions? This is a negative example because I replaced dog with something nonsense like with, and the with dog, yeah, the model should say, no, this is a false context. It didn't happen. This is negative. Okay, so this is the binary task we're trying to solve, just to make it very clear what we're solving here. And how we solve it is we somehow somehow model the context. I just put it here like, well, we model the context somehow. Then we take the previous word and the after word, do this lookup, somehow get them together. I don't know how yet. We'll decide it. Then we take this word as well, represent as an embedding vector, and then we need to combine the context and the target word somehow, and maybe add some hidden layers and then the sigmoid afterwards. Okay, so this is we're simplifying the narrow language model to learning embeddings. Any questions? No. Okay, good. So yes, you have one. Negative. That's why I don't blackboard anything more than single letters. No, actually, yesterday we did a softmax derivation. Yes, you have a question.
If I take out a word like B, my chances of choosing randomly from or a similar word from this thing we had earlier are pretty high. So it doesn't break that anything.
Okay, I don't have an answer. I mean, that's empirically it's been shown like this frequency. You're still here in this issue, like this sampling and frequencies. Well, so there is some rewriting here in word2vec. Yeah, if your target word is this some sort of frequent word, the chances you sample another frequent word is high, but obviously it's not a bad thing. I don't know. I mean, like logically it's doing something which shouldn't be done like badly, but yeah.
Logically, it's a good thing. We want the samples we have more often in the corpus. We wanted to train more often. So
that's true. Yeah, that's true.
So we want to have a lot of examples where we have V and we predict V, because it's really.
That's correct. But I guess the question was like if you by chance replace the positive target word with some negative target word, but which is also positive.
I think there are a lot of positions where you wouldn't put V.
Yeah, for instance. Yeah, that's the point. Yes. So empirically it works. I mean, there's an assumption which is somehow like you just create a negative data, and of course I think you can go crazy about like how you sample your negative examples. You can really do. I mean, it used to be part of research, maybe still is part of research, how to create negative examples for self-supervised learning if you create an artificial binary task, and you might wanna pretend maybe sampling some synonyms if you know already what synonyms are. Maybe you want to do that, but maybe it's too costly, and you just let it run for billions of examples, and it will go out very well.
In principle, I can select any word as the thing I want.
Yes. Yes. Okay. You can select basically what you can select is any word here, like a negative, because you're saying, well, yeah, maybe it occurs in the document, in the training collection, but I don't care, just random word. Most of the time it will be something else. All right, so this is how we're gonna build it, like not theoretically, but some sort of like simplifications. Okay, so remember we had this again, like what we did here. We turn narrow language model where we had this previous words and the next word, and we concatenated them and used some 2 hidden layers and softmax to predict probability distribution of the vocabulary, to predict the next word, which is here the correct label was bark, so one-hot encoding. We turn this very good machine for language modeling turn into something much simpler. So we ditch the Markov property. We say we're gonna actually predict the middle word, and we simplify the softmax because it's computationally expensive. So we're gonna create an artificial task, which is either taking a correct example, a positive example, which will be S1, or negative example, which will be of 0. So if you train this model, what will we predict? I mean, it's it's useless. Like prediction of this model in practice are useless. If you have a language model, it predicts the next word, so you can do auto-completion. Prediction of this word of this model are useless because it just say, well, yeah, this word is most likely to be in this example. That's it. So we're not using this model to predict anything useful. Typically we have supervised machine learning. We learn some task and then we do that, then like put it in production and inference. And if you train a sentiment analyzer, you will sell it and it will do you will make money and will be predicting on new data the labels. Here, if you train this model, there is no added value. So the only thing why we're actually doing this is to train these embeddings, to train better representation of words. Okay, so it's something to remember. Like the model is useless for production or for anything by that because it produces like 0 or 1, saying the word most likely will be in this context or not. But the true value of this model is during the training, it learns these embeddings. Okay. All right. So now let's come to one of the famous word embedding training algorithms, which is called word2vec. Anybody heard of word2vec before? If you have done anything with NLP, you perhaps heard it. So what we're going to do in word2vec is make it even more simpler, right? So we had these hidden layers before. So this remains the same as on the previous slide. We have some hidden layers and so on. We don't care. We remove all the hidden layers. And what we are stuck with is basically a log linear model. So where there will be some, okay, so here will be a linear projection from this to a single. So here comes some dimensions and what comes out is a single scalar. Okay, so there will be one single linear projection, but no more hidden layers. Okay, we don't care about it. Maybe we don't even need that. Let's see later. So we don't need multiple hidden layers with nonlinearities in there. We just make it simple log linear model. Okay. Why? Why should we do that? Say again? We don't care about the model only about the embeddings, only about the embeddings. That's true, but the model also needs to be function properly in a way. But you're right. I mean, we are more, this is interesting and the hidden layers are not interesting, but maybe more hidden layers would learn better embeddings. So I would say yes and no. There's another reason. Somebody was raising her hand. Why we make it simpler? It's a very pragmatic reason.
Because I didn't check a lot of words that possibly fit in there, and it would take too much time to have it very complex.
It's gonna be very much faster. You reduce complexity, you remove layers, you make faster learning. So which means you can, instead of training on 1 million tokens, you can train on 10 million tokens. And that's what you want. You want to really make it fast, iterate it over a large number of these contexts. That's what you want. So this is like practical reason. You make it simpler, less parameters, less depth, super fast training. Okay, so this is one thing. Now the question is like, how are we going to? So here's a couple of question marks, right? I mean, these are, I don't know the function, model, the context are somehow combined. We need to specify them, like how to do so. So first question, let me see. Yeah, okay, so it's how to model the context. So we need to solve this. So here we have 2 words. Okay, so what is sanity check? What is this again? You know this. You get a bonus point. Yeah, 100 encoding. Exactly. You get 0 bonus points now for brevity. What's coming out of here? What's coming out of V of the lookup? What is it? What is it going to be?
The projection in our new space,
which is? Is it a vector matrix, a scalar, a thing? So what is it? Again, this was a lookup operation. We had this embedding matrix and we take so it's going to be a row from the embedding matrix, exactly, which is a vector. Okay. So if embedding matrix, it has a dimensionality of V times D, then this will be of dimension D. So it's gonna be vector in dimension D. Sorry. It's gonna be vector in dimension. Okay, so here output of D is a vector, and this is another vector. Oops. D. So what is the simplest way of modeling the context if I have two vectors? How can I stitch them together? The most easiest thing you can think of. Super simple thing. I have two, yes. Exactly, I can concatenate them, and we had this concatenation in language models before, or something which is almost as simple. You have two vectors of the same dimensions. What can you do with them? You add them together. This is the simplest solution you can think of. You just add them together. So plus and the other, and you have it. Yeah, that's great. Why is it important? Maybe because the operation of this, like the lookup of the target word, is also like R and D. So I cannot write B and D. I'm sorry. Yes, R and D, which means then when we combine them later on, we will have the same dimensions. It might be also, important thing. So we add them up together. Exactly. Cool. Sum. So we don't even care about like the average word of backs. Average back of word embeddings. We just sum them up together. Okay. So this is just summing up two vectors, which means here's coming RD, and here's also RD. Okay. So we call this as a continuous back of words. Why is it continuous back of words? Again, it's taking the embeddings of the words, but just add them together. So there is no differences if the word was before or after. We don't distinguish that anymore. We just sum them together. What is it doing also? If you think of like graphically or geometrically, so we have two vectors. This would be like a vector of D, and maybe this would be a vector of dog, like the context ones. So the summation is, what is it doing? Like it creates, yeah.
It puts the end of the first vector onto the beginning.
Exactly. So this is the resulting vector, right? It's making larger by sticking these together. So it will have some implications later on, as we will see graphically. So we don't normalize it. If we had an average back of words, we would basically scale them down, and there will be some scaling down. We don't care. We just sum them together, because now we have two vectors. So we have one vector of the context, and we have one vector of the word. And we wanna, so what we say, we wanna kind of give a positive feedback to those words which are coming from the similar context, and we wanna penalize words which are coming from untrue context. So how can we combine these two things together? Remember, so similar context should be high score, and different context should be different scores. And we're talking about vectors. So the answer here is the dot product. That's why we talked about dot product quite a lot at the beginning. The dot product is here. Because what is it saying? If it should learn that a word, the target word, should point more in the direction of the true context, right? Because the dot product is there positive, and positive after sigmoid is close to 1. Okay, sorry. No, it was my, okay, let me just reiterate again. Okay, so what we're doing is the dot product, right? So we take this vector in D, and this is also in D. Why I'm writing B, it's D. Sorry, this is maybe R, D. So these two vectors, and I'm creating a dot product. So what's coming out of, what's the range of dot product? What's the domain of the dot product? The dot product's outputting something. Is it the multi-domain arrays? Is it the vector? Is it matrix? Is it a scalar? What is it? A real number, yes. Okay. What is this? A sigmoid. What is coming out of sigmoid? Between 0 and 1. Okay, cool. So, and also, if you're coming into the input of the sigmoid, if it's where do you get more 0 from sigmoid? If your input is where? What is sigmoid again? Yes.
I guess below 0.
Exactly. So this is something like sigmoid. So the more negative you are for sigmoid, the closer you get to 0 of the output, right? So here's 1 and here's 0. So the more negative you are, you're getting closer to 0. And the more positive you are for sigmoid, you're getting close to 1. Which means, and the true label is 0 or 1. What's the meaning of the true label again here? So what was 1 here for this word embedding training? We created this task. What was the 1?
We found this one example where the context had this word in it.
We said it's true, so it's the true context. And this was the untrue context. So it means if we come back here, okay, loss, and so we need it here, the sigmoid should produce 0 for untrue context and 1 for the true context, which means the input. So for true context, we need something which is super large positive number. And for untrue context, we need something which is super large negative number. Does it make sense? Because now, I mean, if this is very negative, it's gonna produce 0, and this is what we want to be for the negative examples. If this is very positive, it's gonna be more to 1, and it should be true for the positive examples. So we want this to learn to be output of this dot product very positive for true kind of true context, and very negative for the fake context. Okay, and that's why it works together with the dot product, because remember the dot product, it's saying like if two vectors are more similar, no matter how long they are, if they're more similar, pointing to more similar directions, their dot product is going to be positive, unbounded, but positive. And if they're pointing in different directions, it's going to be negative. So this is learning that the words should be represented in a way, if they are in their true context, they should learn the embeddings to kind of represent this true context, and they should represent also the negative context. They should unlearn that they are in a negative context. We're pushing these embeddings to learn that this will somehow really capture the true context or not, through this dot product. Okay, it's kind of nice trick actually. I don't know if they thought about it like that, like Thomas Nikolov and others, like 2013, their papers. Maybe they did. It doesn't look like in the papers. It looks like, yeah, we just use this projection and stuff like that. But it has like geometric meaning as well, and it's kind of interesting to understand it, how it works. So it's kind of pushing the vectors of these embeddings far away if they come from different contexts, and try to push them to the same context. Okay. And the only learnable parameter is the embedding matrix E. So and what is the sigmoid of that doing? We just discussed it right now. Okay. Any questions? So now everything is blue. As I said, the only green thing is this thing. We don't learn anything in between. There is no linear projection. I mean, this is the only linear projections basically, but there's no weights to be learned or nothing. We just multiply these things together. We're projecting. Maybe there's another meaning. Let's not go there. I mean, you can think about it, what it means really, this dot product again. But we're just learning the embeddings, and it should learn the embeddings in a way that it can distinguish the true from the false context. Okay. Could you implement it? We had this. We built this tiny little framework already, and I'm almost sure we could implement it with. Well, I mean, we don't have this. Okay, we need to implement this embedding matrix. We're not going to do that because we need the scalability to learn embeddings. It needs to run fast. It needs to run fast and for a long time. So it won't fly with our tiny little Python project. But in theory, this is a product of matrix. This is summation node. This is some sort of dot product node. And we have everything. So we could implement it. Like this is a computation graph. You can really build it from scratch. And actually, this has been built from scratch in this famous word2vec framework. So again, I guess here's just summary of what we are talking about. Let me see what we have here. Oops. Okay. So we train the network to distinguish good word context from bad ones. Yes, we discussed that. We create a set of correct word context pairs and a set of D bar of the incorrect. So this is what we are discussing, like you take the correct and replace the incorrect. So this is D and D bar. The goal of the algorithm is to estimate the probability. Yeah, what? Okay, sanity check. Where is this probability coming from? Why is there a probability right now? Why do we didn't talk about probability, we said like 0 or 1. So why is there a probability here? Because we have something in the network which creates probabilities. What is it? Why is there a probability? Yeah, because we have sigmoid. Sigmoid turns numbers into a probability. That's it. Yeah. So it's saying, oh, the probability probability of being true. We have two categories, and it's saying like, oh, probability of being true given the word and context from the correct set, and it should be high for pairs from D and low for should be 1 actually, or high close to 1 for pairs from true context, and close to 0 for pairs from the negative one. So this is basically, summarizing the discussion we had so far. And by training, oh yeah, okay, so this is maybe a little bit of details of the training, but basically we're trying to locally, as in any other training, supervised training, we have this data of positive and negative example here, and we're minimizing the loss, which is the which is the categorical, which is a binary cross entropy loss over data over our training corpus. So this is a formula which I guess you don't have to remember now. I mean, it doesn't matter because you're showing the examples one after one and trying to make the loss as small as possible of your training data, and you do it in batches and so on. So this is a standard sort of training. Okay, the trick here is the sample. Okay, the trick here, there is one trick, is that we have these positive examples, D, and then we have these negative examples, D bar. And you might think, okay, so how many negative examples I need to sample? How many of them? Like, is it one positive or one negative? That could be like the first choice. It turned out that it's better for learning the embeddings to have much more negative examples. So we want to, for example, we want one positive example and 20 negative examples. So for the same context, you take like the wild bark loudly, and you create the wild dog bark loudly, and 20 random examples for the same context. So the k times more. The k is a hyperparameter, this side. 10, 20, I guess it was 20 in Wörterweg. Yeah, something like that. Okay, so it empirically it showed to be better to have more negative examples than the positive ones. All right. Yeah, so we can do it even simpler or much faster, or just relax the assumption completely. So here's another. Okay, let me just come back here. I think we need to. So Wörterweg was the algorithm from Thomas Mikolov and others in 10 years back, and Wörterweg it's a name for I think they call it the algorithm which has two variants, and one is this continuous back of words, CBOW. So continuous back of words, which is this summation here. So this is one option, how you take the context and sum them together. So it's a CBOW, continuous back of words, Wörterweg version. They said also, well, maybe we can make it even more simpler, the context, and do one more thing, which they call Skip-Gram. What is it doing? So instead of, okay, so we have a previous word, we have the next word, okay? Each of them is again projected through the embedding matrix. So this is the same thing. So now we're, this is coming in a RD. This is also RD, and everything is basically RDs. But then you don't sum up the context together, but you just take each single context word, the previous one and the next one, separately, and make the dot product with the target word. So this is the target word. Make the dot product separately for each word, and each run through a sigmoid, and for each compute a loss. And again, this is saying whether this is coming from the true context or not. So you're decoupling. Before that, we are coupling the context into the sum, right? We are coupling the previous word and next word together in this sum and then did a dot product. Now we're decoupling even more. And this is a relaxation of this assumption. We're saying, yeah, I don't care. I just take the previous word and make a dot product here. And I take the next word and make a dot product here. And each of them will be separately kind of evaluated on the loss. Well, okay, how do I do loss? I do maybe 1 over 2L. I need just one variable, but basically, or even I can train multiple models. Yeah, why not? I can train multiple models on that. That's what I did, I guess. Okay, so this is even more simplification. I'm just saying what I'm saying with this. Do you have an interpretation of that? So before that, we had the wild bark loudly, and if it's a dog, should be positive. What we are saying now, instead of this modeling assumption, we're saying something even more simpler. So before that, we have the wild barked, just below, just barked. And we said before, okay, so this is the target word, and the previous word and the next word will be in the context. Now what we are saying, yes? The target word. Yeah, you're right. We're actually saying any context word now will be positive example. So now we're saying wild dog is 1, barked. So this is the output barked. Dog is also 1. Before that, we had somehow wild plus barked and dog was 1. Like we sum up these two vectors, and we had this before. But now we're saying, yeah, just any word which appears in the context will be taken positively. It's very relaxing assumption. Like imagine you have the first like language model sequence of words and the next word. We say, okay, let's look into the future as well. Okay, let's take the context before and after, but a sequence of words and model them together and throw it in the back. Now what you're saying is, don't even care about like all the words. Just take each of them words separately and say, well, does this word, the word dog, being seen in context of the wild barked loudly or not? Interesting assumption, right? I mean, it's really coupling just a pair of words together. Empirically, it works beautifully. If you learn this, you learn very good embeddings.
Work for large context. But the previous one I would expect to be able to deal with larger context.
Yeah. So the question, like how large the context should be, you can design it as you want, like 5 words left, 5 words right. So there's some. Do I have the details on that? Yeah, choosing the context. Okay, so thanks for the bridge to the next slide. So what is the task? What is the context for Skip-Gram or continuous back of words? And it's been shown the smaller the context. I think I don't have these numbers, but I would point you to this paper by Thomas Nikolov, 2013, like one of those. So he had a couple of papers back in those days, and they were showing that if the smaller the context is, the more like syntactic embeddings you learn, like the similarity will be more syntactic or maybe like on a morphological level. The larger the context you get, the similarity will be more like topical. So, the words which come from the same topic will be similar in this embedding space, right? Because you're taking more global perspective on the words. So words that appear together, like in sport, will be somehow more similar than words that appear in like stock market prediction stuff. Okay, the more closer you get, the more syntactic you get. If you're more interested in, I had a lecture, like an extra lecture on embeddings with let's say syntactic dependencies or multilingual word embeddings. So I think this lecture was like 1 year ago, 2 years ago. So it's on YouTube, so you can watch it. We had a full like look at the slide. So it's on a GitHub, where we also show examples of these embeddings in different contexts, and you will show how they you will see how they behave differently in different contexts if you're interested more. Okay, I didn't put it here because it's somehow like word2vec and word embeddings are still somehow relevant, but there's better models like transfer models which give contextualized embeddings. So we don't spend that much time on that, but there are properties of that. Okay. So empirically, I mean, Skip-Gram model doesn't make any sense. Like from the language modeling perspective, like, yeah, what is it? Like, why should I just predict the word just based on other word next to it? Where is this Markov property? You know, and stuff, yeah?
I think it actually serves a purpose because if we have context where dogs bark and where dogs are wild, but they are never combined, can now say
Exactly.
it's possible.
Exactly. You're giving signal for just concurrence of two words together here in this Skip-Gram. So you're making it more robust. Yeah. Linguistically, it makes no sense, but from the perspective of modeling context, it makes more sense because you get more signal. Exactly. So robust. Yeah, thanks for the point. All right. Well, we're talking about, okay, so we still have some time to finish. We'll finish on time today, as always. So we had word2vec. Okay, so they ignore, so word2vec takes words. So we are talking about, subword units before. Did we like tokenizing, and did we talk about what was that? Oh, sorry. Can anyone remembers we're talking about subword units, byte pair encoding and sentence piece encoding? I guess we had it in lecture 2 or so, like where you basically don't cut your text into tokens by white space, but cut them into like subword units, like maybe letters, and then you combine letters to have the vocabulary and stuff like that. Okay, now it rings a bell. Okay, so we talk about it like subword units. The standard word2vec didn't work, wasn't designed to work with subword units. It was designed to work with tokens, which means you tokenize your text, but then you have two words like, let's say, nice and nicely, and there are just two distinct words, and then the embeddings are different for those two words. They don't share anything. I mean, they will be similar by learning, but they don't share anything by just, well, it's on morphology by taking in an adjective and making an adverb, but something like where you have morphologically rich languages. Okay, so what is well, how about German? Okay, schön und schöne, is it a morphology? Creating like adjective of the oh, I'm not a linguist. What is it like an adjective, and then you make it like a second form of like having a but like this, nice and nicer. Okay, like nice and nicer and nicest. It's on morphology. Okay, no, I don't know. But you have languages which have a lot of morphology. Okay, what was it like? Tenses, past tense. So you just change. You have the same root of the word, but change the suffix. So this is morphology. I cannot come up with any examples in a language except of Czech, which you maybe don't understand. So Czech is like, Slavic languages are super rich in morphology. So you have, yes? Maybe, yeah. I mean, I don't think it's maybe a more morphological thing as well. But like inclination is so you have four false in Germany. In German, you have four false, like dative. Oh, I'm not learning this. Sorry, I can't record this on YouTube. Everybody will be laughing at me. So second, no, is it something like that? Like you have accusative, dative, and two others, right? Okay, so the Czechs have 7 times 3 times plural, singular, and stuff like that. So you have like single root, and then you have like lots of suffixes of these words, and you can just create quite a lot. So it's morphologically like a rich language, but they carry the same meaning. So there is some information in the root which you should somehow infer for all these variants of the morphology, and don't treat them as similar words in your vocabulary. That's what I'm trying to say. You have like a lemma in your vocabulary, which is the basic thing, but then all these kind of inclinations part you don't have in the vocabulary. If you yes, Finnish, Finnish, exactly. Who speaks Finnish? You speak Finnish? Yeah, Finnish is also super morphologically rich. It's even like what I've heard like is the hardest language like morphologically. Yeah. It's crazy. It's much worse than Slavic languages. Anyway, exactly. So then, if you want to work with more morphological languages, you might want to go into yeah, you have rare words and stuff like that. You are gonna go into subword units. So what are you gonna do, or what people do? Piotr Bojanowski, Edward Grave, and Thomas Mikolov in their tackle paper, they introduce the fastest embeddings. And what you want to do? It's they model each word as a bag of character engrams. And then for each character engram, it has its own embedding. And you represent the word as a sum of engrams embeddings. So I'll show you an example on the next slide. So you have a word, oh, okay, eating. I think it's called gerundium in English. Like you have eat and eating, which is the same word, but it has different tense, like simple tense and this gerundium form in a whatever. I'm eating like the process right now. So you would basically create all the sub engrams for maybe 3 to 6, that's what they did, of the word, and they introduced this special starting, characters. So EA, so starting character EA, eat, ate, tin, ink, ng, and end character, then for N of 4, and so on. Okay, so there's basically all the possible sub-character engrams from the word. Then how you represent eating is basically some of the embeddings of these engrams, right? You take all these embeddings, sum them together, and you get a meaning of the whole. So it's taking somehow into account, like you can combine vectors together and the summation should carry meaning of the parts of it, right? So maybe if you have like, this embedding will be, this embedding of this phrase will tell you something about the syntax, like this is a gerundium part, and this will be quite a lot about the meaning of the word, like to eat. So if you have different contexts, like eat it, it's not wrong, it's I ate. But if you have, it's a bad word, something which is, another word which doesn't change form in the past tense, you would learn that like, if you had a word eat it doesn't exist. But if you had like theoretically the word eat it, the meaning of that will be still the same. And then after combining these two together, you would learn something like the meaning is a little bit different because it is like past tense form. Okay, so this is the idea. Yeah.
Work.
Yeah, thanks. Work. You have working and worked. D, right. So you use some of the embeddings, and there are some embeddings that tell you something about the past tense, but the core message is kept. Okay, cool. So this is basically how they created the training data. This is the only thing you change for learning the embeddings is that you don't have tokens anymore in your vocabulary, but you have these character engrams. So your vocabulary grows a little bit. That's fine. But then what you do, you take the same thing and you train it with a Skip-Gram and with a negative sampling. So the same as the training in Word2Vec. You just basically a little bit change your training data, change the granularity of your training data, but the mechanism behind is the same as was in Word2Vec. And you get much better, much robust representation, and maybe even multilingual representation of words. Okay, so that was an achievement. Do I have more on that? No. I was talking about like the simplification thing. I just want to mention that, like the code of Skip-Gram and this thing, whether you can, can you build it and stuff like that. So the original code of Skip-Gram is this simple log-linear model. So everything is just one file of C code. So Tomasz Mikolov wrote it as a one C code, basically everything hard coded here, all the network, because it's such a simple model. You can do it like in a very efficient way. So the efficiency here played a role, and I think they use the same C code even for this subword embeddings fast text. So the idea is you really have huge training data, which gives you much better estimation of the embeddings. Okay. So advances in limitations of word embeddings is something we need to tackle, and then we'll finish. Advantages. So how can you use word embeddings? Now we have word, which is not anymore a one-hot encoding, it's a vector. And they have these, the analogical meaning. So when you have these vectors, you can really solve the task of Queen and King and Paris and France. You can do that. If you download Word2Vec and play around with the embeddings, it's solving this task, like the analogical task. It's very cool. So the similar vectors have similar meaning. If you sum them up together, they will get, this is really nice arithmetic with vectors. But we use them typically as a semantic input to any neural network instead of one-hot word encoding, right? So now you basically do a lookup operation of each one hot, and you get an embeddings vector, and that's what you stuck into your neural network, whatever it's going to be. It's also like instance of transfer learning, which means, so this is a concept for machine learning where you pre-train, so-called, or self-train on some other auxiliary task. So in word embeddings, the task was, is this word coming from this context or not? But then the result, the learn parameters, you plug into some other complex model, and then use this as a pre-trained weights of the other model. So you pre-train on something which you have unlabeled data for. You can create a lot of data by self-supervision. And once you pre-train these weights, you put it into something which you have like fewer training data, maybe labeled data, but you have some information already learned about your parameters. It's very popular. Now, nowadays, everything you do with, well, not with ChatGPT because you don't train ChatGPT. But before ChatGPT, if you fine-tune ChatGPT or fine-tune BERT models, we'll come to that later, it's transfer learning again. So example, you can represent the document as an average of its words embeddings. Okay, so continuous back of words, and you can use it for text classification. So, and also like the word embedding, so it's a historical note, like these were one of those driving forces of the wave of deep learning in natural language processing, like 10 years back. This is great. So you can use also word. Okay, so where can you use word embeddings? Don't look at the slides now. You can use it for search actually. So for example, you're searching for, because similarity means also like maybe synonyms. So if you search for a term, maybe maybe the product which is in there, you may be searching for a product somewhere in the shop, and maybe it's not the same product, but something very similar should be returned instead. Something, you're looking for similar products. Okay, so here's an example of early adaptation of word to vec, where Oren Kurlan, Anna Stock, and the third author used this word embeddings approach applied over the entire corpus of which search is performed, and we select terms that are semantically related to the query. So they had a query, they search in the database, in the corpus, and basically the closest embeddings were returned as the answer to the query. So what can go wrong with that? Yeah. So I did this actually earlier this year, and I was searching for COVID tests. Yes, I think like because until March we had to have COVID tests, something like that somewhere. So if I search in ReveShop for COVID, it returned me Corona Extra beer and stuff like that. Why? Obviously, somebody used pre-trained word embeddings, and in these pre-trained word embeddings, yeah, sure, if you train on news, COVID and Corona is the same thing, right? I mean, there's in similar context.
It makes sense because some person could remember that there is a beer named after, or at least named the same as Corona, and maybe wouldn't remember if it was Corona or COVID. For Rewe, it serves a purpose, I guess.
For COVID, but if you're looking for a COVID test, yeah, maybe. But if you're really looking for a COVID test, it shouldn't give you beer. I mean, this is, Yes. Well, I didn't try that. I mean, I was laughing like, yeah, this is like word embeddings. If you just, yeah, we have word embeddings, let's plug it in. We do like KI. Okay, cool. Yeah, but this is the example where KI is kind of once you get so far. So you need to, it's like, because you're measuring like cosine dissimilarity between two vectors, it's not saying, well, is this a replacement? The problem they need to solve is like, what is the best replacement for a thing that we don't have, but this is a negative example. Anyway, so it can be tricky. So in many other cases, this is a real example, Reve, I think March 2023. And now we can finally solve also like the word analogy task. So Germany to Berlin is French too. You can express it as an embedding of Berlin minus embedding of Germany and plus embedding of France. It gives you a vector right? But these are vectors. Vector minus vector plus vector gets you another vector. And then if you look in the embeddings for a vector which is closest to this vector, you find Paris in the embedding space. So this is pretty cool. And the same for the king and queen. And as we're asking about more like syntax-based and other embeddings and context. So this is the link to the lecture, which I gave 2 years back. So this is cool. This is really doing some nice arithmetics. You couldn't do it just by, how could you create training data and stuff like this. This is a beautiful byproduct of Word2Vec doing this arithmetic. There is more reasons why it's working like that. I recommend Yoav Goldberg and Omer Levis paper, Tackle 2015, if you're interested in that. Anyway, there are some limitations. So we never talk about similarity because words are similar just if used in similar contexts. We just say like, yeah, they're going to be similar. Is it syntactically similar, meaning-wise similar, whatever similar? We don't know. We just say similar. Distributional hypothesis, we don't care. So this is very operational definition. Unfortunately, antonyms, so words which have opposite meaning, like buy and sell and hot and cold, they tend to appear in similar context here in embeddings. Because, yeah, things that are hot can be also cold, and things that are bought can be sold. So if you learn word embeddings from a corpus, you will learn that they are similar, but they're just opposite words. So this is one of the drawbacks. So they tend to judge antonyms very similar to each other because they are in the same context. This is like one of the drawbacks of that. Another is the biases. So they reflect the usage patterns in corpora which they're based on. And the corpora which are based on, they reflect human biases in the real world, like cultural and otherwise. So here's a beautiful paper from published in Science, actually, so very high-profile journal. And they conclude that word embeddings encode not only stereotypical biases, but also knowledge, are problematic as toward race or gender, or even simply vertical, reflecting the status quo distribution of gender with respect to carriers of first names or first names. So if you look into biases in language models, you will find it used to be like that. So if you type on Google, if you search images for doctor, you will see like white males. If you search for nurse, you will see females. Stuff like that. These are biases which used to be in Google. I mean, they're, of course, they change it and work on that. But all these biases, like, that maybe men are more associated with something, whereas women are more associated with something else, it will be reflected in the embeddings because it's learned on data and the biases are already in the data. So be aware of that, okay? And now we have the polysemy, okay? So this is like the same word have obvious multiple senses. And the typical example you're giving here for polysemy is a bank. So a bank could be a financial institution, could be a side of the river, could be things you sit on in a park. So it's a bank, yeah. And a star could be like an abstract shape, or could be like a superstar, or something on the, something that you look up to. The thing is that for each of them, the projection you're doing through the embedding space, you're using a single vector for each of them. So you cannot really distinguish the meaning of those. A star will be always one single vector, and you don't take the context into account here. So it will be problematic with the polysemic words. A bank will have one vector, no matter what the meaning of the bank is, okay? Bank could be 3 things or 4 things, but it has only one single embedding vector, as we just learned. If you use Word2Vec and these methods we're talking about, there's just one single embedding vector for the word bank. That's a drawback. And we're going to finish right now. So takeaways. We introduced self-supervised training for the word embeddings. And we have 2 methods so we introduced the Word2Vec train, where we introduce the negative sampling. So this is a very nice trick, which makes it super, super fast, super efficient, because we don't care about predicting the next word. We care about predicting learning embeddings by predicting whether the word comes from the true context or not. Very simple model. And we introduced 2 things, how to combine the context, which was continuous back of words and Skip-Gram. And if you don't have any questions, this is it. We made it on time. Yes, you have a question. Okay, sorry, no, maybe not.
Can you just go back to slide 34?
Yes, 34, absolutely. 34, yes.
If we look at a sentence like I am blank at the University of Paderborn, for example. So the word STEM that could go there is working and studying. So work and study, and I think it would be a positive example for both. But does it also learn that there should be a form with ing at the end, because we are putting in the ings there, and there should only be examples.
You lost me in the second sentence. Sorry. So can you? Okay, you have the example.
The question is, does it also learn the grammar? Because if I have a sentence, I am blank at UPB, there should only be examples with an ing form in this place. So does it also learn that the probability of I am work at UPB is not probable?
Okay, this is a good question. So you will here you had the word working, and if you split it into these things, you would have multiple ones. So and you skip-gram, so you combine each of these subgrams as a positive. Yeah. So there is a lot of noise in the positive ones. Yeah. So it will learn maybe that the context M has something to do with ing forms. So it will learn syntax, and also it will learn something about the work, like I'm work, and maybe with other words as well. Yeah. So this is something it takes into account, like the syntax. You were saying you had the answer to that.
More or less, it's a language property in that case, and we can distinguish the ing spoken in the engram. So yeah, we probably learn it, but I don't know. Maybe we don't.
Because in the third lecture, it was, I guess, we also talked about reducing words to only their stem or because.
So here you're exactly. So you can stem the words, but here you just say, I don't care about stemming. I just take everything which I get and learn everything as much as possible. Okay, cool. So if there's no other questions, thanks for the signal, and have a great weekend.